Well, hello, friends, and welcome back to the show. Today we are going to profile the profiler in Serenity because yesterday I was profiling the web browser running the ray tracer demo thingy, and the profiler itself was loading the profiles real slow. And I got some comments saying, hey, it seems like you should be profiling the profiler. And yeah, it's something that's kind of biting me back because for years I've been complaining about other profilers saying like, oh, I wish they would use their own profiler to profile their own profiler and things like that. And now it is my turn to put my money where my whining has been. So we are basically just going to start by profiling the browser, and then we profile the profiler loading the browser profile, and then we see what's going on and we try to fix it. So I guess the first thing we'll do is we'll grab that same profile of the JavaScript ray tracer thingy. So let's see, profile PID21 enable, boom. Oh, dang it. It's the JavaScript heap logging. I'm just going to turn that off. I always forget. Maybe there should be a runtime way to turn this off. But if we don't turn it off, then it will make the profile all weird. So let's try that again. Pro ps if browse. Okay, and then we go to the right place. Ray.js HTML path. Okay. And then we'll make a copy of the profile, browser profile. And the interesting part now is going to be we're going to make a new profile, because I guess we can load this one first just to see what it looks like. So as you can see here, it takes quite a while to open up this profile. Quite a while. And yeah, we definitely don't want it to be this slow. So now what we're going to do is we're going to profile opening the profile viewer. So we'll make a -c, which is run this command with profiling on. So now the kernel is recording what's going on. And then we can just close that. And now we have PV profile. So let's look at the profile viewer profile. And I guess we don't need this part is like when we close the app. So let's only look at this stuff. So there's like 11 seconds worth of samples. One sample is 1 millisecond. So we can actually see what it's doing here. So this is all the time is in load from file. And then very, very top heavy here in lfloater symbolic key. Very, very heavy in symbol count. Well, that's immediately stands out as strange because the symbol count in an elf executable does not change. So we should only need to call that once ever, basically. But I guess that we probably call it repeatedly, and then it has to actually go and look up the symbol table section in the program, that we're profiling, and find the number of symbols. So where are we doing that? Actually, we can see here where we're doing it. Elf image section. Okay. So where's section? So this guy right here is calling, wait, that's not symbol count, that's section count. This guy calls section header. Okay, I think maybe the tree here is lying to us a little bit, but because I don't see a link between those. But regardless, we can definitely stop calling symbol count so often. Oh, wait, I was reading it upside down. Symbol count calls section. Yeah. I'm so used to inverting the tree that I didn't realize I had not inverted the tree. So symbol count calls section, yes. That's how our time is being spent. So first thing we'll do is we'll just, when we make an elf loader, so the way that we use elf loader, I'll show you in the profiling tool, or in the profile viewer, is when we are here, we are in load from perf core file. That's the function that we're in. So what we do is, first we open the profile, which is a JSON file. I can show you what they look like. I guess we'll show the, what was it called? PV profile, yeah. So this is what it contains, just all the samples in JSON, basically. And at the very head of the file, I think we probably can't see that here because it doesn't go all the way back. I wonder if our head can handle this. Yes, it can. So here you can see that it has the executable, the path to the executable that this profile is for. And that's how we know where to look for the symbols. So what we do when we open it in Profile Viewer is we map that executable in memory, and then we make an elf loader object and just wrap the executable data in an elf loader. And then we can ask the elf loader to figure out what symbol is this, like what is the name of this function at this address. So elf loader internally stores an elf image, and elf image is the elf object. It sort of represents an image, and it knows how to find the different sections and headers and things like that. But loader is a slightly higher level object, so one thing we could do here is we could just say like cached symbol count or something, or even just symbol count, and then we can just compute that right away after, or like when we construct, because here now we have an elf image, so then we can just do symbol count is an image symbol count. And now whenever you ask the elf loader for the symbol count, we can just give you the cached number instead. Wait, what's that thing? Toggle bookmark. Okay, I don't know what that was. So right away, this means that we can get rid of, inside elf loader, we can like just replace any call to m image symbol count with m symbol count. And it's very possible that this will make our whole problem go away. Wouldn't that be nice? Because it looked really heavy, but we'll see what happens if we just make this change. It's probably not our whole problem. I shouldn't say that, but it looked pretty bad. So let's see, how are we going to do this? I guess we can, let's make sure that we save that browser profile. So let me mount the disk image here and copy out the, what was it called, browser profile. So we'll copy that out and make sure that we always have that in our home directory. Like that. All right. So now if we rebuild, it'll be way faster to get a new profile, basically, because we already, otherwise we would have to first generate the browser profile and then profile the profiler, loading that. But now we can go straight to the profiling the profiler, loading the browser profile. Anyway, it's a good thing that we're putting our money where our mouth is, because We should do that more often. So let's see how long it takes to load it now, just with this one change. Okay, well that was significantly faster than 11 seconds, but I guess we'll get a profile of it. We'll learn exactly how. Oh, look at that. That is actually not bad. So we're down to 2.4 seconds, 2.5 say? 240, no, 2,467 milliseconds total. But symbolication is still up top, but look at that. All of that action that we were wasting in symbol count is fixed. It's gone. You don't see symbol count anywhere here. It's fantastic. So now what do we have? We have 1 second spent in symbolication, and then seems like the rest of it is like JSON parsing, and there's also like building the profile tree. Profile frame append. This one might be avoidable, but I think let's focus on the biggest one. So the biggest one is Symbolic Key. And here we are spending the time in Symbolicate and then demangle. And this thing here is in the it's the C++ demangler that comes with GCC. So this thing is not in code that we control. It's one of the very few things in Serenity that we don't control. It's like stuff that comes with a compiler. We actually used the compiler's version of a few things. Like name demangling is one thing, and then stuff like 64-bit division and modulo, things like that. If you have like a 64-bit integer and you're compiling for a 32-bit platform, and there's no native instruction in the CPU for doing like multiplication or division, then the compiler has like these functions that does that for you. And in our case, that's how 64-bit math is implemented on Serenity behind the scenes. Anyway, we can see here that demangle, actdemangle is actually creating a string every time. And that's the heavy part of symbolication. So let's look at this Symbolicate. Maybe we can cache these. Because if you think about the way that we use Symbolicate, basically for every one of these samples, so every line here, or every step in this timeline, represents a single sample. And in literal terms, a sample is a backtrace, so like a stack trace. So it has just a bunch of addresses of functions that call each other. So if we go like to the innermost part here, like this guy right here, he has one sample at this particular frame. That means that this exact sample is this exact stack that you see here from the start down all the way to this guy right here. And in the case of start, there are 2,428 samples that all started with the first frame being start. That means that we have resolved the start symbol name at least 2,428 times. And then if it occurred later in the stack trace, then we would symbolicate it again. So I think basically we're symbolicating the same names over and over. So we can definitely do less of that. So symbolicate, there's a different version depending on if you're in the kernel or if you're in user space. Because in the kernel we're trying to conserve memory a little bit. Because we mainly do symbolication on process crash in the kernel. And also if you go and look in procpid stack, so if you open up a program that you're running here and then you look at the stack, then what's it doing? Then you can see backtrace, and this is the kernel generating this backtrace for a running program. So you can get these for any program. And selection up here is broken at the moment. I think that's because of index invalidation in the table view. I need to look at that later, but anyway, when we're doing symbolication in the kernel, then we want to use less memory. So maybe caching demangled names is not a priority there. Whereas in user space, it's okay to cache. So we're using this thing called a sorted symbol. Let's see. So the first thing we do when we're asked to symbolicate something from an outfloater is that we generate a cache of all the symbols. And the cache is, wait a minute. This cache, so we walk the entire elf image, get all the symbols, and then put them in address order, I think. That's the whole point of sorted symbol, is to use quick sort all the symbols by address. Because that allows us to do a binary search when we're looking for a specific address. So actually, maybe sorted symbol could just store the demangled name instead of the name. Oh, I see why it's not doing that, because this is a string view, so it's not storing a string at all. It's storing a string view that points into the elf image memory. That's why it's done that way. So I think we'll just do this. If not defined kernel. So we're running outside of the kernel, and then we'll have a string demangled name. And then we can do this lazily. So this is where we're doing, this is the binary. Wait, this is not a binary search. Okay, this could be a binary search, but it's not. It's a linear scan. Apparently. I thought it was a binary search. Room for improvement here. So we're scanning the symbols from 0 to the end of the symbol table, and then looking for the place where the address that we're looking for is greater than the symbol table address at that entry, because that means that we are somewhere within a symbol. Because normally when you symbolicate, then you're symbolicating at an offset, because you when the kernel samples the process, it doesn't necessarily sample the process like at the very first instruction in that function. Rather, you're like somewhere inside the function at some random offset. So that's why we have to do this little thing here where we check, well, are you inside of this symbol? Anyway, so I think basically this here is where we determine that, okay, this is the symbol, and then we're going to return a string for that. So what we'll do is we'll just say if this is the kernel, we'll have two variants here. So if it's the kernel, then demangled name is demangle symbol.name. See, and then we can just return that down here. But if we're in user space, then we'll say that demangled name is actually a reference to symbol.demangled name. And if demangled name is null, then we will demangle it and cache that. Yeah, exactly. So symbol.name. So On subsequent requests to demangle the same name, we'll just reuse what we already have. Okay, I think that will get rid of that. So let's try it out. We're missing something in brace in it somewhere here. So let me show you what the symbol table usually looks like. So here's an unceremonious symbol table for the kernel. You just have an address and a name for that address, and here's what kind of symbol it is. But ignoring that, for symbolication purposes, we just look at the address we're told to symbolicate, and we scan forward through this list. Say that we're looking for 184 here, right? So then we're scanning like da, 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 and then 184 is 184 is not. No, we're looking if the symbol table address is greater than the address. Okay, so here we don't stop here, but we stop here because this guy has passed 184, which means that we go one step back and say, okay, you are an offset into ACK-string repeated, if you know what I mean. Anyway, let's see if this is faster. I think this is going to be a lot faster because we were probably doing the same demangle over and over and over. So okay, wait, I couldn't tell if that was better or worse. Browser profile. That's pretty snappy. Let's get a profile of it. Obviously, we gotta get profiles. And die. Okay, so now we are in 1.8 seconds, down from what, 2.46? That's pretty good. And as you can see, demangle is not at the top anymore. Symbolicate and demangle is like way down. So we were doing very aggressive repeated demangling basically. It's good. So now instead the JSON parser begins to shine, begins to dominate. We can see here JSON value from string is just the recursive parser of JSON. And this one, I think it's harder to do a targeted fix here. We would need something more architectural, but it's definitely possible to do better because it's quite allocation heavy, the current design. We might be able to get something here if we can avoid some allocations. Let's see what those are. Vector of profile. What are they called again? Profile : frame. Just vector of frame. All right. So we have an event object and it has a vector of frames, and appending to that guy is actually showing up here with 2% of samples. So is that avoidable? I'm just wondering. Where do we append? Append here. So event frames append. And event is constructed here. So this is walking the stack array, and for each event in the JSON, I think we can pre-compute the size of this so that we don't have to allocate multiple times. That might be helpful. So we can see here that this loop goes from stack array size -1 to 1 going backwards. So conservatively, like if we pre-size this guy to the stack array size, ensure capacity, stack array, values size, or can we even do dot size? Yeah, I think that's just a shorthand for that, yeah. So maybe we can pre-size it and avoid multiple calls. Because vector append will grow a little bit at a time, the vector. So I think it's sometimes like if you have an empty vector and then you add or append over and over, if you know how many times you're going to append, you can tell it up front, hey, I'm going to append this many times, because that avoids the dynamic growth algorithm that otherwise has to sort of grow. Every time you call append, it has to check, oh, do I have enough space for this? Otherwise I have to realloc. So now we're trying to skip that part, or skip directly to the final size to see if that allows us to avoid some extra mallocs. So let's just get our profile straight up. Browser profile. Okay, that's pretty good. And prop profile. And I feel like that got worse suddenly. So where are all of those? Here are the calls to ensure capacity. What happened here at the end? It just started shooting up. I don't know, that didn't work out as well as I thought it would, so maybe we should backtrack. Why did it do that? It's so weird. I guess since we're going from size -1 to this, we can actually skip over one of these guys. So did I just make it a little too big, maybe? I'm just a bit weirded out that it got slower from this. All right. It's a very strange thing here. Wait, what is here anyway? Okay. Fine, let's go back to the way we were then. Not quite sure why that would be a pessimization, but I'm not going to argue with numbers. Browser profile. Okay, now we're in the 2000s again. Wonder why we got that good 1.8 second one. Maybe my computer is doing more stuff now or something. Sometimes it's like that, like you get like one really good one, and then because of some outside factors, you don't know what it is exactly, and it's hard to reproduce the numbers. Unfortunately, with this kind of thing, there's a fair amount of noise, right? Like you have the scheduler in the operating system is always introducing like randomness, or at the very least non-determinism in your profiling. It's very, very hard to get exact reproductions of profiles. So yeah, maybe that was not as successful as I was hoping, but what else do we have? This guy is read from disk. Yeah. But we can at least see that most of the time is in loading, and actually, I guess we didn't really look at this. We have a lot of self-time in load from perf core file. So self-time means that it's not like something that it's calling that's taking up the time, but it's this function itself. So I guess we can take a little quick look at what it's actually doing. Unfortunately, we're not able to drill down into like instruction level profile here. That would be a cool future addition to profile viewer if you could see like assembly level details. But we know that we're in this function, so and we have a loop here with a loop inside of it. So I'm guessing that it's the nested loops here that are heavy. And what are we doing here? We're doing gets on JSON objects. We can see them here though. Dun, dun, dun. Yeah, I mean, there's nothing obvious that sticks out to me at the moment. Wait. What is this even? Why are we passing putter to this guy? This seems like, I don't think we're hitting this code path, but it seems extremely unnecessary to create a new string every time, or you can also just do that. Because there's no format string actually happening. I wonder, are we doing a lot of string construction here? String construction. We have a fair amount of string construction. It's like 1% or so of the profile. Yeah. So you could definitely dodge that if you pre-create all these strings. So that would be one thing we could do, just as an experiment. So we could say like, could use fly string even. Key. Oh wait, let's commit the thing we already had because I don't want to lose that in the noise. So this guy right here. Oops. DevTools. Profile viewer. Oh, don't. Oh, an unnecessary call to string. Okay, why can't I put the spaces in the right places? All right. And then libelf, we're just caching the symbol count. Caching the symbol count and caching the demangled names, which is a huge improvement. So, oops. Libelf cache image symbol count. Cache some things. Cache the symbol counts plus demangled names. User space. To make repeated symbolication requests faster, now cache the symbol count on elf loader instead of looking it up in the image each time. We also cache the demangled versions of names after after looking them up once. First time. This is a huge speed up for profile viewer. Okay, that's pretty good. But let's look at these keys. I think we can probably get some more improvement here. So, because right now, JSON object get takes a string as the key, and since we're passing a literal here, this means that we are constructing a heap string every time that you do this. So we're doing this once for every event in the profile. So we can just move these out. So we'll call them fly string malloc key. Malloc, and I wanted timestamp. Type, I don't know. Not the most exciting change here, but kind of speculative also. We'll see how much this can help. Putter key. Size key. Putter key. Stack key. Alright, we just need free key as well. Getting a little freaky here. Okay, and oh, I guess we could actually cache these guys. So these could be like question marks. Oh, oops, we'll store that up here. Right. So will this help? Basically, this should get rid of all that string construction that we were seeing in the profile, since we're moving it out to before the nested loops. But we'll see how much it actually helps. Because it was only 30-40 milliseconds, something like that, right? Browser profile. All right. So load from perf core, they're basically gone, but there were not that many of them anyway. So, yeah. I think I'm gonna say that this one is a little bit on the side of uglification for the sake of micro-optimization. So this I would consider not worth doing because it makes the code uglier. So a better approach, I think, here would be to take the time to write an overload here that takes a string view, for example, and then you can pass a string literal to it without constructing a heap string. And then it would need to be plumbed all the way down so that the hash map inside of the JSON object knows how to do a lookup without having a string. So that will take some more time to do, but yeah, for the sake of like code aesthetics and just maintainability and everything, this type of thing, not worth that tiny improvement. Because what, we got like 30-40 milliseconds. It's 1 point something %. So we're skipping this one. But I mean, we should have known that since we saw that it was small. I guess I just wanted to check it anyway because we have all this self count here, and I don't exactly know what's causing that huge self count. But I don't have a way to see that with the current tools, so it is what it is. Anyway, I think we're still got a pretty huge improvement here, down from what, 11 seconds or however much it was when we started to 2 point something seconds to load the profile. I'm gonna call that a success, and I guess we'll probably want to improve on this in the future, but for the moment this definitely makes the profiler a little bit nicer to work with. So I'm gonna end the video here for today. Thanks everybody for hanging out, and I hope you saw something interesting, and I'm glad that we decided to put money in the mouth, or whatever the expression is. So now I can once again say I think people who make profilers should profile their profilers sometimes. I can say it for a while at least, and then I'm going to have to profile again. Anyway, thanks for hanging out. I'll see you next time. Bye.